The Navier-Stokes equations are famously hard, and most of that difficulty comes from a single term, viscosity. It's the friction inside the fluid, and it's where turbulence and chaos hide. So here's a tempting question. What if we just cross it out? For fast-moving flow away from walls, that isn't cheating. It's the right model. And one of the most useful equations in all of physics drops straight out of it. Start from the momentum equation for a fluid. Density times the acceleration of a parcel equals minus the pressure gradient, plus the viscous term, mu times the Laplacian of velocity plus gravity. 4 pieces, inertia on the left, and on the right the 3 forces, pressure, friction, and weight. That friction term is the one we're after. The Laplacian measures how much a parcel's velocity differs from its neighbors, so mu times it is the drag of the surrounding fluid, smoothing out differences. It's also the most expensive term, second order in space, dissipative, and the place the tangled, turbulent behavior comes from. So let's set the viscosity to 0 and see what survives. The friction term vanishes. What's left is density times acceleration equals minus the pressure gradient plus gravity. Continuity, the conservation of mass, is untouched. These are the Euler Equations, Navier-Stokes, for a fluid with no internal friction, an ideal fluid. When you allow to throw friction away, compare its size to the inertia term. Inertia scales like density times velocity squared over a length, the viscous term like viscosity times velocity over length squared. Their ratio is density times velocity times length over viscosity. That's the Reynolds number. When it's large, and for an aircraft or a river it's enormous, the viscous term is tiny next to inertia, and Euler is an excellent approximation. Away from walls at least, hold that thought. Take steady, inviscid flow and follow a single streamline. Along it, the momentum balance reads density times velocity times the rate of change of velocity equals minus the rate of change of pressure, minus density times g times the rate of change of height. Now notice that velocity times its own rate of change is just the rate of change of 1/2 velocity squared. For constant density, every term is the rate of change of something, so the whole bracket is constant. 1/2 density times velocity squared plus pressure plus density times g times height stays the same all along the streamline. That's Bernoulli's equation, and it came straight out of dropping viscosity. And it's everywhere. Bernoulli explains how wings lift and how a venturimeter measures flow. The Euler equations are the backbone of aerodynamics, of gas dynamics and shock waves, of weather and ocean models, and of fast simulations that skip the cost of resolving friction. For the bulk of a high-speed flow, ideal is good enough. But ideal has a famous failure. Solve inviscid flow around a sphere, and the pressure comes out perfectly symmetric, front to back, so the net drag is exactly 0, a ball that never slows down. That's D'Alembert's paradox, and it's flatly wrong. Because right at the surface, the fluid must stick to the wall. In that thin boundary layer, the velocity changes so sharply that viscosity, however small, dominates. So the real picture is Euler almost everywhere, plus a thin viscous skin at every wall, where the drag and the separation actually live. So, crossing out viscosity turns Navier-Stokes into Euler. For fast flow far from walls, it's an excellent, cheaper model, and it hands you Bernoulli for free. Just remember the catch: no matter how fast the flow, viscosity always wins at the wall. That's all for this video. Tell me what you want to see next in the comments.